Welcome to the second lesson in autonomous robots. So today we'll be talking about the science of making robots move, that is kinematics. Just a brief introduction as to what we did in the last session, that is session 1. So in session 1, we talked about the introduction to the field of autonomous robots itself. We talked about the different components that make up a robot, both in terms of the electromechanical hardware as well as the software modules that go inside modern robotic, over the state of the art in the field of robotics. So some examples of current research in this field includes swarm robotics, humanoid robots, and stuff like self-driving cars. And finally, we capped off last week's session with a small demo on a popular robotic simulating software called VREP. And yeah, so that's what we did in the first session. So in this week's session, we'll be talking about the science behind making robots move. So that science is called kinematics, and you'll eventually be implementing your own robotic kinematic solution on a simple differential drive robot in VREP. Okay, so, but before going into what kinematics is all about, there are a couple of definitions and notations that you need to know in the field of robotics itself. This will sort of help you out, when you're reading textbooks, just to be familiar with what's going on. And once we get that out of the way, we'll then head off into what kinematics is all about. We'll talk about the different types of kinematics. That's basically forward and inverse kinematics. And then we'll have a small discussion on the kinematics of a particular type of robot called a differential drive robot. So this is a very simple, this is perhaps the most simplest robot out there. And we'll finally cap off this session by showing you a demo on VREP and how to move a differential drive robot. Okay, so if you look to the figure on the right, you will see that it's a figure of a 3-link armed robot. So you can see that there is link 0, link 1, and link 2, and link 2 is essentially an end effector. So these are links, joints, and your end effector constitute your mechanical components of a robot. Your links are nothing but rigid bodies. And the electrical or electronic components of a robot include actuators and motors. So actuators and motors are basically things that allow motion between two links. So I always, whenever I'm discussing about robots, right, I always bring up the concept of how robots are analogous to humans. And you can sort of see it in this picture right here. So you can think of a link as like a human that enables motion as your elbow, and you can think of your actuators as the thing causing the motion, like your muscles, and finally you have your end effector, which is your hand. So in actual robotics, your end effector sort of depends on the application that you're sort of working on. So for example, if you're working with a robot that does some welding tasks, your end effector will be a welding gun that the robot holds. So it's also important to note that these definitions don't just hold for an industrial armed robot. They also exist for mobile robots and UAVs, etc. Although things will obviously look different. Okay. So
kind of lost you there at the beginning.
A couple more definitions that you need to know. Okay. You mean the starting of this?
The starting of the next slide.
Starting of this slide or the
next slide? Next slide, yeah.
Oh, okay. Yeah. So there are a couple more definitions that you need to know before we get into what kinematics is all about, and they're basically simple definitions. So whenever you're working with robots, right, you have to know what is the operating environment in which they're working in. So that is defined by your configuration space or your C space. So simply put, it's like a mathematical definition of a robot in its operating environment. And the number of notations used to describe the C space of a robot is called the degree of freedom of that particular robot. I'll sort of get into what this means in the next slide, but yeah, it's just a simple definition. Your workspace is very similar to your C space, but it is specifically defined for your end effector. So if you recall from our previous slide, your end effector is like a very specific tool that your robot is working with. The C space of a ground robot operating on, say, even a flat ground is given by a three-dimensional vector. So your X, Y, and theta. So your X and Y basically tell you the centroid of the robot. And your theta is basically needed to provide information about the orientation of the robot. So is the robot facing north? Is the robot facing south, east, west, southeast? So with these three dimensions, you can basically denote the operating environment of a mobile robot operating on the ground. Now, what happens in the case of a UAV? So a UAV or an aircraft is obviously slightly more complex than a mobile robot. So you'll have to have more definitions to describe the C space of a UAV. So it turns out that the C space of a UAV is like a 6-dimensional array. So you have your X, Y, Z, and you have three orientations, your angular orientations. You have your roll, yaw, and pitch. So I hope you understood how a mobile ground robot is a 3-dimensional C space, has a 3-dimensional C space. You need X and Y to determine the centroid of the robot, and you need theta to determine the orientation. In the case of a UAV, like I said, if you're playing like a video game with that involves flying, you can note that you can control your plane in 3 ways. You can control your roll, which can basically make your plane, do a barrel flip or a barrel roll. You can control your yaw, which can basically turn this fin, sideways, and you can sort of make your plane turn left or right. Or you can make your plane pitch. So you can bring the nose up or bring the nose down. So in addition to these 3 dimensions, you also have your X, Y, and Z. So your UAV has like a 6-dimensional C space. Okay, so with all the definitions out of the way, I think we can sort of now, introduce the concept of kinematics. So kinematics is basically the study of motion. It doesn't necessarily, pertain to robotic motion, but in motion in general. And when we're talking about kinematics, we usually don't talk about the forces behind these motions. We just talk about the equations of motion that, generate, that cause the thing to move, the thing under study to move. That's it. So kinematics is basically is your first step to, studying autonomous robots. Autonomous robots, their main characteristic is that they can move without human intervention. So you have to know how they move. And that's what kinematics is all about. And the second point of studying kinematics is that kinematics sort of acts as a sensor. This is something that you'll see in the next lesson when I talk about sensors, but you can think of kinematics as a way to determine where the robot is at any given time. Once you know how your robot moves through certain equations of motion, it becomes much easier to know where the robot is. Okay, so before talking about the 2 different types of kinematics, which is forward and inverse kinematics, I'll just play a small video of a Tesla robot charger. There are a couple of things that I wanted you to note from that. One is it does seem pretty cool, but this yeah the first major thing is that you could see how it sort of like I would say sort of struggled to get into its final destination. So this is a sort of a theme that you should keep in mind. Uh, to perform human-like tasks, it's very difficult for robots to do that. Uh, you'll have to use all the modern algorithms to achieve some level of human intelligence to robotics. And the second thing that I would want you to keep in mind is that this particular robot knew where its end location would be. Um, so it basically knew that it had to go here. So that is something that I will explain in the next slide. But just keep in mind that for this particular problem, it knew its end location, and its goal was to arrange itself uh, in the most possible optimal way. Okay, so now with that point in mind, I'll bring the definitions of the two different types of kinematics into the picture, and that is forward kinematics and inverse kinematics. The two ways in which you can cause motion in your robot. So all robots that you see operating, right? They all either follow forward kinematics, or in most circumstances, it's inverse kinematics, which cause them to have their motion. So in forward kinematics, this is the problem statement. Suppose you know all these joint angles. So you have link 0, which is say at 90 degrees with respect to the ground, and you have link 1, which is say at an obtuse angle with respect to link 0, and you have link 2, which is say at another angle with respect to link 1. So if you have all these three angles at a given coordinate frame, say at the coordinate frame of the base, can you compute the coordinates of this end effector, this point right here? So that is the forward kinematics question. The inverse kinematics question is merely the reverse. Suppose you are given this end effector right here. If you are given the x and y coordinates of this end effector here, can you rearrange all these three links in some way so that we can get these three joint angles? So the example of the Tesla charger that you saw right here was an example of your inverse kinematics. So because you knew the final destination, you knew the x, y, in this case also z, coordinates of, say, the charger right here. What was the way to optimally arrange all these links in terms of their joint angle? So that is an example of an inverse kinematics problem. Obviously, the inverse kinematics problem is much more complicated than your forward kinematics. There's a small link that I would like to show you. A GUI that shows you how inverse kinematics is in a sort of intuitive way. So, oops, okay. Just click on inverse kinematics here, and you have your workspace and your C space. This is, yeah, you can recall from the definitions of what they are in the previous slides. So let's see what this inverse kinematics is all about. So if I click on this point right here, so you can see what the robot did, right? I gave it the end coordinates of where its final destination should be, and it rearranged itself to meet, to ensure that its final coordination was met. So the algorithm determined that this was the most optimal arrangement to reach this final destination. So if I click here, and so I gave it an endpoint, and it found out that this configuration was the optimal way to reach this point. So that's essentially what inverse kinematics is all about. And if you want a better understanding or an even simpler explanation as to the relationship between your forward kinematics and your inverse kinematics, you can refer to this simple picture that I created. So theta 1 to theta n basically refer to all joint angles of your robot. So it would basically be in this case, you will have theta 1 to theta 3, theta 1, theta 2, theta 3. And your x, y, and z are basically your coordinates of your end effector, which is basically this. So your forward kinematics basically transforms this given data into this, and your inverse kinematics transforms this given data into this.